Hello everyone, I'm here to talk about elastic potential energy and our upcoming lab. Just to review with you a little bit about elastic potential energy, I have a falling ball that you guys have seen before. When this ball falls, it's going from gravitational potential energy into kinetic energy. Once it reaches the height of the floor, it has no more gravitational energy and it's entirely kinetic. But something interesting happens when that ball impacts the floor. It starts to deform. And that's one of the two most important parts when it comes to elastic potential energy. Deformation is any change in shape. And what sometimes happens when an object changes its shape, it stores some of that kinetic energy in the form of potential elastic energy. Now, deformation is only half of it. This ball is going to impact the ground, deform greatly, but it still has some rigidity. It has some resistance. It takes some force to deform this ball. Because it has some rigidity, it's able to store that energy that it had while it was deforming. If it had no rigidity, like a wet noodle, it would deform and it would just stay in the shape that it changed to. But this ball likes to go back to its original shape. So as I play this video and the ball slowly comes down, it impacts the ground and we have the start of deformation. When that ball deforms, it flattens out on the bottom. And when it flattens out and squishes the most, that's when it's most deformed, and that's when all of that kinetic energy, because it stopped moving downward for a moment and hasn't started rebounding back up yet, for a moment, it is all entirely potential energy because of at this position right here, it is no longer going downward. It hasn't started going back upward. So it has no kinetic energy. There's a moment where it is not moving, but it's entirely deformed. All of that energy is now in the form of potential elastic energy. Now, going from here, let's talk about what we're going to do in our lab experiment. I've set up a data table for you, and it's a pretty basic data table. And I'm going to put in data for you for 4 different types of balls. That we're going to do the exact same thing that you saw in this previous video. We're going to take the balls, but we are going to measure their ability to store potential elastic energy in them and re-release that potential energy back into kinetic energy. We're going to basically see which ball bounces back up the highest. For each ball, you can see we're going to do 4 total trials. Don't worry about the averages currently. I'm going to teach you how to do an average on a spreadsheet the next day that we work on this. But for now, you're just going to do your 4 trials in a row. Now, there's a certain way we want to do this with each of these trials. And I got my son to help me out with these trials. So this is Christian, and you can see one time through basically what we did. I'm going to rewind this a little bit. What I did, I took a meter stick, and with that meter stick, I made markings on the wall every 10 centimeters using masking tape and a marker. Now, you may not have a yardstick or a full meter stick, but we do need to measure this in centimeters. So your data is going to match my data. So hopefully you have a ruler at home that you can measure out every 10 centimeters. You can make a marking on the wall because truly it's these marks that I use to do my measurements. Now, my measurements aren't going to be perfect. I'm going to be kind of guessing what number it best matches because you can't see these numbers on this meter stick. That's the important part. You need somebody to film this for you. Either have one person drop the ball and you film, or you drop the ball and have somebody else film for you. Now, some of you have slow motion mode on your camera on your phone or your parents' phone. That would be great if you want to use a slow motion. I did not. I used regular speed, and as long as I play it back, I could scan back and forth. Notice I always start my ball drop with the bottom of the ball at exactly 1 meter or 100 centimeters up. Now, if energy was perfectly conserved inside this ball and didn't go out into the floor, didn't make a sound, and it didn't have any friction whatsoever, this ball would totally bounce right back up to the original height. But it doesn't. This ball doesn't have all that much rigidity. It deforms a lot, and it's unable to store all that kinetic energy. And some of it's converted into heat energy through friction, and there's drag in the air, and it's making air particles in the room move around. But as I scan this thing downward, I could really see how high this ball bounces back up and make a really good estimate. And that looks like about the peak of its bounce back right here. So you can see this number is 40, that one's 50, and I would estimate this ball bouncing back up to about 43 centimeters, I would guess. And I've done this for several different types of balls. So I could show you my next one. So that was the emoji. That went up to 43 centimeters. I would then do that trial again 3 more times in a row. Once again, I'm going to leave that average section blank for now. So do the ball 4 times in a row, then move on to your next ball. The next ball is a yellow Nerf ball. Let's see if that's this one here. Yep, there's the yellow Nerf ball. You can see that one did not bounce back very well at all. It has very little rigidity to it. It deforms a lot, but it doesn't spring back to its original strength with much force. So this one did not bounce all that high. So my son dropping it from 100 centimeters again, let's estimate how high that thing bounced back up. And it looks like it didn't even reach the 20 centimeter mark. I would estimate that to be about 17 centimeters. So if I go back to my yellow Nerf, I would estimate about 17 centimeters on that one. Let's try our next one, which I think might be a soft soccer ball. It's the same one I use in my social studies class to pass around the room when somebody wants to decide to read. For this experiment, let's see how well this one bounced. Anybody who knows this soccer ball is in my social studies class realizes it's really soft and squishy. Not much rigidity. It does deform a lot, but let's see how well it bounces back. And this one beat that Nerf ball slightly, barely higher than that one. The peak of its bounce back is just under the 20. I'm going to call that about 18, maybe 19 centimeters on the soft soccer ball. Now, I saved the best one for last because I have this really weird, super squishy ball. And as you can see, this is not changed in any way. This ball deformed so greatly, it's like a wet noodle. That ball from 100 centimeters literally just splats on the ground because of lack of rigidity. Really strange. You can see it had no bounce back at all. That's going to be difficult to find a ball that has that little rigidity and deforms that much. It stores no energy. All that energy was dissipated through, there's like little rubbery spheres inside this ball. It's almost liquidy on the inside. So it really dissipated that energy throughout it and made that energy go into the floor and other places as well. Energy can't be destroyed. It has to be someplace else. So this ball literally has no bounce back. So that's an easy one to graph. That would be 0 on that one. So what your goal is, I would like you to find 3 different types of balls around your house. Be sure you drop them based on the bottom edge of that ball being at 100 centimeters and record it, see what that bounce back is, and fill in your data. I'll have this data filled in for you tomorrow. My son and I already did this experiment. We recorded all those trials. You go ahead and do the same with 3 other types of balls. Fill in this data table for today, and that will be it. And we will talk about what we're going to do with this data table besides averages on our next instruction day. By the way, this lab, I'm planning on taking about 3 days of instruction to do this lab experiment. So the materials that you're going to need a meter stick or a ruler. If you could only find one with inches on it, you could quickly do a conversion on the internet. You could look it up on Google, centimeters to inches or inches to centimeters actually, conversion. So you could figure out what your measurements would be if you measure in centimeters instead of inches. You'll need a phone with a camera. You're going to need to find 3 different types of balls, like golf balls, tennis balls, whatever you'd like and that you have around the house. Someone to help you film or to drop that ball, and optional, so you can make it much more visible and easier to read on your film, tape for making those markings. Now, I put the piece of tape on a table, and I used a marker on a table, so I didn't smear any of that marker on my walls, because I don't think your parents would appreciate that very much. So, This is going to be our experiment for today. It's called elastic energy in balls.